Hello, my name is Fernando Quiros Pacheco, and in this talk I will be presenting the Giant Magellan Telescope Natural Guide-star AO Control Strategy Review and Performance Simulations. We will start with a brief NGO introduction, then describe the NGO control strategy, present some performance simulations, and conclude with a summary and future work. The NGO wavefront control mode will enable the diffraction-limited imaging and spectroscopy of bright sources for the first generation of AO instruments. The adaptive secondary mirror and the direct feed architecture will enable high throughput and low emissivity, since there are only 3 reflections before reaching the AO instrument in the folded port of the GMT. And AO wavefront sensors, both the natural guide-star wavefront sensor and the laser tomography wavefront sensor, are fed by reflection of the instrument window, and this architecture is replicated in every instrument in the folded ports. It's important to recall that in these AO observing modes, the M1 and M2 pairs of segments must be phased to a small fraction of the observing wavelength in order to reach the diffraction limited performance. In the case of the NGO mode, the image quality requirements in median conditions, it's stride ratio in H band higher than 65%. The adaptive secondary mirror is a segmented one. Each of the 7 segments has 675 actuators. For AO control, we have decided to define a model basis over each of these 7 segments. It is important to note that with this choice of model basis, segment piston is an independent mode that is orthogonal to all the others, and so it can be controlled and optimized independently. The model basis definition of the central segment is different from the one of the outer segments. There is a central occultation of 3.6 meter due to the shadow of the M2 baffle, and so there will be a total of 108 unilluminated actuators within this shadow. These actuators will have to be controlled as slates following a force minimization criterion that is integrated and part of the model basis definition. The natural guide-star wavefront sensor designed at ENAF Archetry features 2 sensing channels. The first channel utilizes a 92 by 92 subaperture pyramid wavefront sensor with tilt modulation to measure atmospheric and phasing errors at high temporal bandwidths. Because of the well-known sinusoidal response of the pyramid wavefront sensor to segment phase piston errors, its capture range is limited to plus minus half a wave in closed loop. Therefore, a second NGWS channel was needed to detect segment phase piston errors due to this phase wrapping. The NGWS second channel 2013 baseline design used a second pyramid sensor identical to the one in the first channel, but measuring at a different spectral bandwidth to detect the sign of segment piston ejections. In this way, the capture range was increased to plus minus 3 waves. The design of this second channel is currently under revision, and it should enable unambiguous segment phase piston detection using additional multi-wavelength sensing. There will be a couple of talks in the main program of this workshop by Cedric Plantet and Sebastian Haffert on some of the alternatives in consideration. This slide summarizes the NGO control strategy, starting from the main NGO controller that takes the NGWS measurements, the first channel, and computes the high-order, high-bandwidth ASN modal command. We have also the auxiliary phasing controller that uses the second NGWS channel measurements to detect and correct the occasional segment jumps that may occur during bootstrapping or when the sync conditions deteriorate, as we will show later in the simulations. We also have the so-called modal gain machine, originally proposed by Guido Agapito and tested at LBT, which is an online modal optimization comprising two simultaneous loops, an optical gain tracking loop and an optimized modal gain integrator. We will be discussing this in the following slides. It is important to note that this approach enables the non-common path aberration compensation with a pyramid wavefront sensor, and in our case the offsets requests from an on-instrument wavefront sensor will be applied as a modal command reference. The optical gain tracking loop relies on the online estimation of optical gains on a subset of modes. We have selected one segment KL mode over each of the 6 outer segments, and each mode representing a different radial order of the segment model basis. Each of these modes is sinusoidally modulated and injected as a probe signal directly to the ASM. In closed-loop operation, the effective optical gain is obtained after the modulation of these probe signals on the differential command and integrated commands. The effective optical gains estimated at a given iteration of the OGTL loop are then used to compute the so-called optical gain coefficients for the probes using a simple integrator controller. After a few iterations, the OGTL will drive the effective optical gain to the nominal value of 1, that is, the pyramid sensitivity in diffraction limited conditions. Once these optical gain coefficients are determined, we now need to extrapolate to all the other modes, clustered by similar radial orders, and currently we do this interpolation using cubic splines. The optimized modal gain integrator also uses the differential command and integrated command telemetry to reconstruct the open loop model coefficients, time histories, that are needed to compute the optimized model gains using the descent criterion. For this application, a model of the rejection transfer function of the NGO system is needed. The integrator gains of the temporal controller are updated at the same time as the optical gain compensation coefficients. And in order to prevent instabilities in the closed loop operation, large changes in the gains needs to be avoided. This is why these integrator gains updates need to be low pass filtered and scaled by the changes in the optical gain compensation coefficients as well, as originally proposed in Guido's paper. In this slide we show an NGO simulation demo under median sync conditions and with a bright guide star. Once the AO loop is closed, the wavefront error over each segment converges rapidly, and the remaining errors are segment pistons that are recovered gradually by the second NGWS channel. The telescope is now phased. Note that in this simulation we used an idealized piston sensor that behaves similar to the pyramid wavefront sensor in the baseline design, and it took 4 iterations to recover all segments. In this slide we present simulation under variable sync conditions. It starts with median sync and it gets worse down to 1 arcsecond sync. The model gain machine is updating both the optical gain compensation coefficients and the integral gains of the temporal controller at a rate of 1 Hz to cope with these varying conditions. We can see that the effective optical gain is maintained throughout the whole simulation close to 1 as intended, and this is thanks to the update of the optical gain compensation coefficients that we can see they increase as the seeing deteriorates. Also, I showed a snapshot of the integrator's gains for two iterations, iteration number 10 and iteration 49. This is at the beginning of the simulation, this is at the end, and so you can see how the gains are also properly updated by the model gain machine. It's also important to note that as the seeing got worse, we started to see some segment piston ejections from the first channel, and these ejections were promptly recovered by the second channel simulated in the simulation. Some final comments on the pyramid wavefront sensor segment piston stability. We know that at bootstrap, the presence of large low-order aberrations and the phase wrapping during loop convergence will invariably eject segments that will be recovered by the second NGWS channel, and once that is done in steady state, phasing control will remain stable as long as the sync conditions remain also relatively good. That is below 1 arcsecond sync, which corresponds to a freight parameter of 10.4 centimeters. In worse sync conditions than that, the pyramid wavefront sensor can no longer stabilize segment piston. And we have noticed that phasing stability in poor sync is partly due to island modes developing on the on-axis segment. And we are currently evaluating reconstructor regularization to try to improve the island mode control and phasing stability. In summary, high-fidelity NGAO simulations have allowed us to perform image quality verification and algorithms validation. We have adopted and tested in simulations the model gain machine to cope with changes in observing conditions. While this detailed analysis concluded so far that the NGO mode will meet its image quality requirements in the majority of observing conditions, the robustness of the NGO segment piston control should be improved, in particular against strong atmospheric turbulence. A critical trade study on the design of the second NGWS channel is currently underway, and the performance of the selected design will be verified on the high contrast AO testbed. There are several talks on this workshop in the main program in this regard. Thank you very much.